So far, so good. Okay, I've put up on the home page, you guys can see the computer. I wanted to tell you that I have added that resources that I told you about. This is a trig reference sheet for you guys. This is the isograph paper, and I'm about to show you what the isograph paper looks like, but that's a printable isograph paper for you guys. And then the Chicago style of documents for writing papers, it's in there. So hopefully that gets you kind of straight on that part of it. And I'm going to switch over to the document camera now, and we'll go from there. All right, this is isograph paper. I'll scroll in so you can actually see it a little better. There we go. And it's built on a 60-degree triangles. So when you're trying to do 3 dimensions, it's a lot easier to see, and it's a graphic tool that will help you out. Be able to look at the graphs. When we do 3 dimensions, trying to draw those 3-dimensional axes makes it a little rough. All right, Kyle, you're on, aren't you?
Yes.
Oh, sweet. Oh, George, or sorry, George. Sorry, Ed. Ed, turn around and say, wait back, Kyle. We got Kyle. He's here virtually today. Can you see the screen okay, Kyle?
Yes, I can see it.
Okay, great. Okay, and we are recording, so we're in good shape there. So this paper is really going to help you guys out. Okay, couple other little details. I went back in because I opened up the next couple of assignments. So I went and looked at what I actually had set up in terms of how many attempts per question you guys have and what the threshold was before you didn't have to do the adaptive homework. Now, those of you who want to do the adaptive homework, if you test out of the homework, so if you get 90% or better on the homework, it will automatically give you, I will automatically give you the 2 points extra credit for the adaptive homework. So adaptive homework is going to be extra credit points so that you can use those to get you through. So that's what there is, it's there. And so it's set up right now, 3 attempts per question. The threshold is 90%, at least at this point, for the adaptive, not having to do the adaptive homework. And getting, just testing out and getting credit for it. I've got through section 2.5 open. I got through section 2.5 open up in the homework. So now you have several other homework sections that are there. So hopefully that will get you going. Okay, for the example I did on Wednesday, scroll back out. I couldn't remember the picture that I had. We just started with the, here we go. We just started with the kind of forces. Basically what it was is I had a box. So if you think of a raised bed box, it was like this, and the 2 forces were at this part of the lid. So that was the picture that was for the problem that we did on Wednesday. Just kind of giving you an idea of what that picture was. Because I couldn't remember what it was in my notes, and I finally found it. And it's not your problem 220, it was a problem 220 in a different textbook. Because it took me a while to actually find the picture. Okay, so we've been talking about vectors, using the parallelogram theorem for vectors, using law of cosines for vectors. So I'm going to start with a problem here just to kind of give us a way to go. Let's see, it's probably easier to do it this way. So I'm going to have, we're going to start at a point A. I'm going to give myself some references. We're going to come down here, and this is going to be 15 kilometers. This is 10 kilometers. We're going to call this side B. We're going to call this side A. This is going to be the resulting vector, except I didn't draw a nice straight line. This side is C. We are given that this angle right here is 20 degrees. I'm going to give myself some reference points here. We don't know C. This is going to be angle A. This is angle B. And we want to find, and the angle we want to find is this angle right there from the horizontal. So we want to find the magnitude of C, and we want to find that angle. Everybody with me? Okay. So this is going to be a law of sines and a law of cosines type problem. The first thing we have to know, we have to kind of figure out a couple of things. We've got this angle and we've got two sides. Well, we know this angle, that's 90 degrees, and based on that trig identities that I gave us earlier, I'm going to turn that light off. Can you guys see that? That works pretty good. I'm not getting the reflection. So this is 20 degrees. So this angle, so this will be angle C, is going to equal 110 degrees. So if I use my law of cosines, I get C squared is equal to B squared plus A squared minus 2AB cosine C. We can just plug in numbers. I get 15 squared plus 10 squared minus 2, 15, 10 cosine of 110 degrees. And that's going to give me, when I plug in all my numbers, this, I get 100, I get 225, I get 300 times the cosine of 110, and that's going to give me 428 kilometers squared, which gives me C is equal to 20.7 kilometers. So that one's pretty straightforward, right? So now I want to figure out this angle. So the easiest thing to do is figure out angle A. So I'm going to do A over sine of A is equal to C over sine of C. So sine of A gives me A sine of C divided by C, which is now 10 kilometers divided by my 20.7 sine of my 110. So sine of A works out to be 0.454, and A then ends up to be 27 degrees. Okay, there we go. There we go. So A is 27 degrees. And so 90 degrees is going to equal 20 plus 27 plus my question mark angle. So my question mark angle actually equals 43 degrees. Does that make sense to everybody? Because that one was just kind of a straightforward how we can use the law of cosines to get to get some information. Okay, good. All right. Now we're going to get a little tricky. We're going to play, again, we're just playing with geometry right now. Geometry, trigonometry, whatever you want to call it. I've got a box. Okay, I've got a box. And I'm just going to put a dash in here so we've got our image that it's a box. This side of the box is going to be 4.75 feet. This side of the box, as you can see, it's not drawn to scale, is 3.25 feet. And this side of the box is 6.5 feet. Okay. We're going to look at a triangle that's in 3 dimensions. This side of the triangle is the diagonal of the top of the box. This side of the triangle is the diagonal from this corner to that corner, or that side of the box. And this part of the triangle is the diagonal on that part of the box. So each of these are on our box faces. So I'm going to put this in here just so it makes it clearer to see that that's on the box face. And we want to find that triangle, including this angle right there. So everybody know what we want to do. Okay. All right. So the first thing I need to know are the sides of the triangle. Luckily, that's going to be easy to figure out because we're going to use a squared plus b squared is equal to c squared, and each one of those are diagonals. Okay? So for the side that's 4.75 feet squared plus 6.5 squared. Okay, for that side, that one gives me 64.8 feet squared. It tells me that that side is 805 feet. For the side that's 4.75 feet squared plus 3.25 feet squared, that gives me 33.125 feet squared, which gives me a side that's 5.76 feet. And this one, so this one was the 4.75, 6.5, so this is that one. This is 2, that's this one. And then I've got the 6.5 feet squared plus the 3.25 feet squared gives me 52.8125 feet squared, which works out to be 7.27 feet. And that's this one. So I've got all 3 of those. So I can use the law of cosines. So if I do this, I'm looking for this angle. So I'm going to go over here. So this is the 7.27. And this is the angle that I want. So that this is A and that's A. Then this is C over here. So that makes this side the 8. Let's see. The 8.05. And then this side becomes the 5.75. I'm going to find that angle. I'm just going to find the first angle, and then you can find the other ones the same way. So this is a squared is equal to b squared plus c squared minus 2bc cosine A. Cosine A ends up being a squared minus b squared minus c squared divided by 2bc. And that ends up being 7.27 squared minus 8.05 squared minus 5.75 squared divided by 2, 8.05, 5.75. Plugging all that into the calculator, that's a minus sign. There should be a minus sign. That equals 0.486. And so A ends up being 60.9 degrees. You need to follow the same ones for all the other angles in order to define it.
We got a question here in Tonkawa.
Uh-huh.
How do we determine, for the first angle we did, the 4.75 and 6.5,
Uh-huh.
how do we locate the hypotenuse of that?
You mean this one?
Yeah, how did we locate where that goes?
Well, because this is one side of my box, this is the other side of my box, this is the connection for the half of the box.
Okay.
That make sense? Yeah,
Yeah.
because each one of these are on the face of the box, on the face of the box.
Okay.
Okay, we good? You doing okay over there, Kyle? Okay. All right. Okay. So we're still dealing with, I started this up here. We're still dealing with resultant forces. So we're going to do another resultant force problem, but this time we're actually going to show the picture. Okay. We're going to show the picture before we move on here. What we want to do is we want to determine the resultant force for this picture. And the direction. So we want to determine the magnitude of the force. And we want to determine the angle as measured counterclockwise from the x-axis. Now I'm going to do law of sines and cosines for this solution because it's something that we haven't dealt with, and so I'm going to show it from that perspective. And we're going to kind of walk through how to approach these problems. So I'm going to move this over, so I'm hoping to keep it on the screen. So the first thing that you guys have to do when you deal with these things is be able to draw from the picture the information that you need. So we've got a force that's 800 newtons. We've got a reference point, okay? And we have our force that's 600 newtons. Now, remember we said we could move our forces so that we could draw our parallelograms. So I'm going to redraw my 600 Newton force. So this is my 600 Newton force to give me my parallelogram. And I'm going to redraw the other piece of information that I need, which means that this is a 30-degree angle, which now means that this is a 60-degree angle. I'm going to put in the resultant force in a different color. And of course, we don't know if this is to scale or not, but this is going to give us the information that we're after, which means that I'm going to be finding this angle as requested. So everybody see how I redrew from the original picture to the picture that I got? Y'all good for that? Okay. So now you can actually do this. So now I can actually say, all right, I've got my triangle here. Okay. And I'm going to call this side A. I'm going to call this angle C. I'm going to call this side B, and that side C. We know C angle is equal to 60 degrees. A is equal to 800 newtons. B is equal to 600 newtons. So if I want to do C squared is equal to B squared plus A squared minus 2AB cosine of C. This is going to give me 600 newtons squared plus 800 newtons squared minus 2, 600, 800 cosine of 60 degrees. When you do this, this works out to be 1 million minus 4,800. Gives me 5,200, 520,000. Gives me C is equal to 721 newtons. Okay? I'm going to find this angle using the law of sines. So that angle is going to be B. So I'm going to use C sine C is equal to B sine B. Sine B is equal to B sine C divided by C equals 600 sine of 60 divided by 721 gives me 0.721, which gives me 46.1 degrees. But that's the angle inside my triangle. The angle that I was requested to find is this one. So that has to be, the angle I want to find has to be 90 degrees minus 46.1, which ends up being 43.8 degrees. And for those of you who want to follow it, this is fundamental problem 2-3 in your text. And all the fundamental problems in your text actually have the solutions in the back. We good? Okay. Now, we're going to complicate things. Of course, right? Can't do things that without complicating it. Okay. So sometimes it's going to make sense to move our forces around so that we have the components along the v-axis and along the u-axis. Okay? These are the actual forces, but we may want to know it on these axes here instead of the traditional axes that we want to deal with. And that'll make sense as we start getting into trusses and we start to get into physical things. You know, you want to move these things onto alternate axes to try and keep track. And this looks an awful lot like one of your homework problems, except it's not the homework problem. So what we're going to do is we want to resolve the components of force 1 onto the v and u axes. Okay? We want to resolve those components on the v and u axes. So let's look at it for a second. I'm going to redraw it. So what we've got is this weird axis here where this angle is 75 degrees. We're told that F1 this is our F1, is 4 kilonewtons, and we're told that that angle is 30 degrees. So that means that this angle right here is going to be 45 degrees. So what I'm going to end up with is, and this is my v-axis and this is my u-axis. So if I draw this, I'm going to have FV, I'm going to have FU, this is the vector that I start with, which is my 4 kilonewtons, and we know that angle is 30 degrees. Okay? That angle is 30 degrees. We can use our geometry to tell us that one's 45 degrees. We should use our geometry to tell us that that is 180 minus 45 minus 30, which should give us 105. And you might want to go back to those identities that we did, that I showed way back last Monday. Way back last Monday. It feels that way this week. Way back last Monday. We're only in the first week and it already feels that way. Okay? So now I've got all the angles and I've got one side. So what I can do then is I can do FV sine 45 degrees is going to equal my 4 over the sine of 105. We solve for FV, and that's going to give me 2.93 kilonewtons. And then FU is going to be sine 30 degrees, and that's 4 over sine 105. And so Fu is going to equal 2.07 kilonewtons. So we can split up our force components onto other alternate axes, and that will help us. Remember what we said is that we could shift forces around provided that things were still in the right directions. Well, sometimes by moving them onto these alternate axes, we can give ourselves an opportunity to put those forces in those lines of action. Everybody good? Making sense? We haven't gotten too wonky yet. All right. Okay, so if you wanted to keep up where we are in the book, just keep it up. We're about to start section 2.4. And even though we've already kind of talked about it, because that's how I did problems on Wednesday, let's kind of look at where we're at. So if I have an X and a Y axes, and I have some force here, so this is my force, there's my angle, this is my force that I'm dealing with, this is the Y-axis, this is the X-axis. We can do those projections, right, that I get F of Y is going to be the magnitude of the force, sine of the angle, and F of X is going to equal the magnitude of the force, cosine of the angle. Now, what's going to be interesting is a lot of times you'll get your force vector that's given to you like this. And they'll give you little tiny numbers. This will be A, and this will be B, and that will be C. Now we can redo our trig identities, all right? Because we know that my force vector is going to equal F of X in the I direction plus F of Y in the J direction, but I've got F cosine of the angle, and we may not be given the angle, but we're given that, right? Cosine of the angle, that's our B over C, I, and then F, and if I want sine of the angle, that's my A over C, J. And this just goes back to our trig identities, and it's going to simplify how we look at pictures and how we deal with the pictures a little bit. And if you've been looking at Chegg in some cases, all of a sudden they would get 3/4, or they'd get 2/3. And you're going, where on earth did this 2/3 come from? Well, it came from the cosine, but they're using this kind of a trick. They're using that kind of a trick. The other thing that we know is that the X and the Y, go ahead and throw in the Z, are all independent, and my resultant force in the X direction is going to be the sums of all of the X components. And the resultant force in the Y direction is going to be the sums of all the Y components. And we know that the magnitude of the resulting force is going to be the square root of the Fx resulting squared plus the Fy resulting squared. And that the tangent is going to be Fry over Frx. Again, we're in 2 dimensions right now, but we can do that. So we good? Because we're about to do one. All right? We're about to do one. So I've got, this is fundamental problem 8. I've got 3 vectors. In this case, I'm not going to worry about redrawing the picture. I'm just going to do them. So my first vector, which is this vector, so sometimes, depending on how you want to keep your subscripts, I'm going to do force 250. It's in the negative x direction, so I'm going to put my negative sign there. And there's my 250. I'm going to put in, because of the way these are, I'm going to put in my 4/5 in the I direction. It's in the positive y direction. And there's my 3/5 in the y direction. So I just literally wrote down my force off the picture. Now this one gave it to us at an angle, so this is F400. So F400 is 400 cosine 30 degrees in the I direction. And it's 400 sine 30 degrees in the j direction. And the other one is real easy. F300 is just 300 in the I direction. My resulting force then is going to be, this works out to be minus 200. That works out to be 346. 400 cosine 30 plus 300 in the I direction. And I end up with 150 plus 200 in the j direction. That gives me, this works out to be 446 in the I plus 350 in the j. The magnitude, 446 squared plus 350 squared is 567. And the tangent is 350 divided by 446. And that implies an angle of 38.1 degrees. No major problems so far? Okay. All right.
Is that how we should do problems with reunited?
It depends. You know, it's going to depend on the problem. You know, that's what we've been showing so far. There's multiple ways of doing these problems. Depending on how they're set up, you know, one way might be easier than another. I mean, that's, you know, it's just going to be, it's just going to kind of depend on the problem that you're after. Because the other thing I can do, remember, is I can resolve these two vectors using the line and the cosines, or swap sines and cosines, and then throw in the third one. It just may be an easier way to do it.
I think we may have another question here in Tonka.
Yeah.
Oh,
So where'd you get the 4/5 and 3/5 from?
4/5 and 3/5, right here.
I didn't see that.
Yeah, it's a little hard to see.
That better?
Yeah, I can see it.
Yeah. Yeah, so depending on how they set up the problem, see, you could do this one really easily by law of sines and cosines and resolve this into one vector over here and then add the two that way. That's another way to do it. So it's just going to depend on on your situation and on what the problems are that you have. Okay. Well, I'm going to introduce the three-dimensional system here because that's what we do. So if I've got a vector in three-dimensional space, you know, we're using our unit vector I, our unit vector j, our unit vector k. Ultimately, what we're going to get to, guys, is we're going to define a unit vector along whatever vector we're having. We're going to ultimately get to that point. But now you can also see the ISO paper. So let's look at the ISO paper. You can start to see it, you know, this ISO paper. If you look at the way they've got this part, that's what you've got here. And it makes it a little easier to see the individual components. Okay, it's going to make it a little easier to see the individual components. Especially when we start dealing with things that are in three dimensions and you want to drop down that projection, you'll be able to see the planes a little bit better. And the author of our book is drawing in the planes. So here's our vector A, and we talked about this before. So this is going to be our AZ, right? But then we have a projection of A onto the XY plane. Okay, there's my projection of A onto my XY plane. So we'll start to see that. So we can look at this a little better because I actually printed out our figures from the book. So you can start to see it. So there's my AX, here's my AY, here's my AZ. And you'll see your AX on both sides. And when you start working the problems, what's going to happen to us is they're going to give you these dimensions by using these little hashtags. So it's going to start showing the dimensions a little bit when we get in there. So it'll tell you the dimensions. So you'll get these planes, and that ISO paper is really going to help you look at the planes. So we're going to start taking three dimensions that are out there. So we get those, and we will have some standard angles here. So alpha is going to be, so there was a reason I did that box triangle, because this is essentially what we've got. Here's my box, right? I can put my box in here. I can draw this, and I have my box first side, and there's my other side. So there was a rationale behind actually doing that problem, because here's the vector that I want to deal with, and this is the defining of a unit vector along the vector that I'm at. So I'm going to have a U of A, which stands for a unit vector, and the whole point of this unit vector is just to give me the direction. The whole point of this unit vector is to give me the direction. So if you want to go into the book to see the pictures, okay, this is figure 224. Because I know it's hard to draw these things if you haven't practiced them. It's real hard to draw those things if you haven't practiced them. And this is figure 225. That's figure 225. And then this is figure 226. But here are the tricks. So alpha is going to be the angle between the section that's in the x1 and the vector A. Beta is the one that's going from the y to vector A, and gamma is the one that's going in the z direction. But the trick is we're ultimately going to work on defining a unit vector. And then to make it a little easier to see, there are the planes shaded in, and this is figure 227 in the text. And I'm going to stop there because I'm not going to have enough time to write out some of the identities. But
Do you
that,
need a sign-in sheet for these students in Tonkawa?
no,
You got it?
yeah, this class is small enough that I know who's missing.
Okay, that's good.
And I've had them for 3 semesters, so I know all of these folks.
I see some familiar faces too.
Yeah. Oh, and next Friday, we're going to have a quiz. So I'm going to have you proctor a quiz for me over there.
Okay, sounds good.
All right, thanks.
Pardon?
I said thanks.
I think we got another question here.
Okay.
That's what it's over.
Do what?
He's wanting to know what the quiz is over.
Pretty much what we've been covering.
Oh, boy.
Yeah, doing resulting vectors.